In today's video, we have one learning goal and one learning goal only. We are going to be determining the oxidation number on each element in a compound that we are given. Sounds simple, but it can take some practice, so I want you to get ready to challenge yourself. Make sure you've got your periodic table handy, preferably the one in your New York State chemistry reference table, but any periodic table would be helpful, and we will get to it. Let's continue to learn about what our periodic table can tell us. So you may have noticed there on the key box of your periodic table, on the upper right-hand corner, there is 1, sometimes 2, 3, or even 4 numbers with a positive or a negative sign before them. These are the selected oxidation states of various elements, and they represent the most likely ions that these elements will form, or the most likely oxidation states that these elements will take on when they are bonded to other elements in compounds. Carbon, for example, has the ability to have an oxidation state of -4. That means the carbon has been reduced, but it also has the ability to have an oxidation state of +2 and +4. Now we could look at an element like boron, and boron only has one selected oxidation state. This is a little bit simpler because that means that if we're trying to figure out the oxidation state of boron, it's always going to be +3. Oxygen, similarly, has one selected oxidation state, -2. When oxygen is involved in a redox reaction and it is no longer neutral, it will always have an oxidation state of -2. Fluorine will always have an oxidation state of -1. It gets a little more complicated as we see elements that have multiple possible oxidation states. And this is where we need to start thinking about how to determine the oxidation state of an element in a compound. Let's talk rules for determining oxidation numbers or oxidation states. Those two terms are interchangeable. There are more than just the 6 rules I'm going to go over here. These are some of the most important and generalizable rules. There are sometimes exceptions to these rules, but these will get you started on the right track. Like I said, I'm going to talk about 6 rules, but really there's only 2 that you need to commit to memory. The other 4 you can reason out using the selected oxidation states of your periodic table. So let's take a look. Rule number 1, free elements that are in their uncombined state, not bonded to an atom of a different element, always have an oxidation number of 0. So what are some examples? H2 gas. Yes, hydrogen is bonded to itself, but it's not bonded to any other elements. So the hydrogen in H2 would have an oxidation state of 0. So would the bromine in Br2, so would the sodium in a solid sample of sodium, so would the sulfur in S8 compound, right? It doesn't matter how many of the same element are bonded together, as long as it's just one element not combined with any other elements, that atom will have an oxidation state or an oxidation number of 0. Rule number 2, monoatomic ions, that means ions that are just made of one element, in ionic compounds have oxidation numbers equal to their net ion charge in that compound. You can refer to the oxidation states on the periodic table for the possible oxidation states of metals or nonmetals in ionic compounds. We'll look at a couple examples in a bit of how to use this rule. Rule number 3, hydrogen's oxidation number is either +1 or -1. It's usually +1, but if hydrogen is bonded to a metal, it can form a negative -1 charge hydride ion. So just keep an eye on hydrogen there. Rule number 4, fluorine, the topmost halogen, has an oxidation number of -1 in all of its compounds. You can see that there is only one oxidation state for fluorine. However, the rest of the halogens, chlorine, bromine, iodine, can have a positive or a negative oxidation state. In general, they will have negative oxidation states when they form ionic compounds with metals. So if chlorine, bromine, or iodine are bonded to a positively charged metal cation, they'll have a negative oxidation state. And each of them only has one option for a negative charge. However, when bonded with oxygen, they can form positive oxidation numbers of various charges. And this is where you're going to use the strategy that I'll teach you in a moment to work out what their charge would need. Finally, rule number 6, in a neutral atom or molecule, the sum of the oxidation numbers must be 0. In a polyatomic ion, the sum of the oxidation numbers of all the atoms in the ion must equal the charge on the ion. So for example, sodium chloride is a neutral compound. It's made of two ions, sodium and chloride, and the oxidation state of one sodium plus the oxidation state of one chloride must equal 0. This makes sense if sodium's oxidation state is +1 and chloride's oxidation state is -1. +1 minus 1 equals 0. H2O, there are two hydrogen atoms and one oxygen atom in this molecule. It is overall neutral. So the oxidation states of the two hydrogens plus the oxidation state of the oxygen must equal to 0. That means one of these elements must have a negative oxidation state, the other must have a positive one. NH3, the oxidation state of one nitrogen plus the oxidation state of three hydrogens must equal 0. So again, we've got to have one of the elements bringing a positive oxidation state, the other bringing a negative to have them equal 0. Let's look at an ammonium ion, NH4 plus 1. So in this case, because we have an overall net charge, when I add together the oxidation states of one nitrogen plus 4 hydrogens, I should end up with +1. Finally, if I have phosphate, PO4 minus 3, the oxidation state of one phosphorus plus the oxidation states of 4 oxygens, when all summed together, must equal -3. We're going to do some example problems now to help us think about these oxidation states. It does take some practice. But the most important rules to memorize of all these rules that we just talked about are Rule 1, free elements always have an oxidation number of 0, and Rule 6, in a neutral atom or molecule, the sum of the oxidation numbers must be 0. The rest of the rules you really can figure out using the oxidation states on the periodic table in your reference table. We are going to determine the oxidation number of copper in 4 compounds. I'm going to do this kind of out loud, thinking aloud with you, modeling how I'm thinking about this, and I've pulled a screenshot of each of the possible elements that we might want to consider from the periodic table, just so that it's right here on our slide with us. So let's start off by thinking about copper all by itself. That would have an oxidation number or an oxidation state of 0, because elements that are by themselves, always have oxidation numbers of 0. Number 2, copper chloride, CuCl2. We are going to now need to do a little bit of detective work here to think about the oxidation state of copper in copper chloride. So in this neutral compound, that means overall the compound has a net charge of 0. One copper ion is bonded to 2 chloride ions. If we look at chlorine's possible oxidation states, chlorine can have a positive oxidation state, but in this particular situation, it must be negative because this is an ionic compound, and so we must have a negative ion bonded to copper, which can only be positive. And so the only possible negative oxidation state that chlorine can have is -1. So if the 2 chlorine ions in CuCl2 both have oxidation states of -1, that means that copper in this neutral compound must have an oxidation state of +2 in order to cancel out the 2 negative charges from the chlorine. So in this case, I have copper with an oxidation number of +2, and I had to figure that out by thinking about what copper was bonded to, what the oxidation number of that substance was, of that element, right? And then thinking about what the oxidation number of copper needed to be to get the net charge to be 0. Number 3, copper oxide, CuO. So I have one copper ion bonded to one oxygen ion. So I have copper, I have oxygen. The only possible oxidation state for oxygen is -2, which means that in this case, the oxidation state of copper has to be +2. It can't be 0 because it's bonded to oxygen, right? When elements are bonded to other different elements, they're going to have an oxidation number that is not 0. And so I can figure out that this one would be +2. Now let's look at copper sulfide, Cu2S. So I've got 2 copper ions bonded to one S ion. So again, I'm thinking about 2 copper ions and 1 S ion. And for this S ion to be negative, there's only one option for a negatively charged sulfur ion, and that would be -2. I've got 2 coppers bonded to one sulfide. So in order for the net charge to be 0, each of my 2 coppers must have a charge of +1. So this would be an oxidation number of +1 on the copper in Cu2S. So notice here It is possible for copper to have an oxidation state of 0 if it's all by itself, of +2, and of +1. And that matches what we saw on the selected oxidation states of the periodic table. Let's check back in on our initial learning goal. Hopefully you feel confident determining the oxidation number of each element in a compound. And do make sure that you feel comfortable moving on, because the next task that we are going to have is to track how the oxidation number of an element changes before and after a chemical reaction. Nice job today.